So today we are going to learn portfolio optimization, and as we start portfolio optimization, we have to know certain basic facts of optimization. So instead of directly jumping to portfolio optimization, the first course, the last lecture of the first week should end with equipping you with tools in order for you to understand portfolio optimization in a better way. And hence today's lecture is on a crash course on the KKT conditions. KKT actually is name of three persons: Karush, Kuhn and Tucker. So these people are responsible to bringing out the Lagrange multiplier rule when you have inequality constraints. What is the Lagrange multiplier rule? The Lagrange multiplier rule that you have learnt in school, in your maybe first year college, of minimizing a function or maximizing a function with respect to one constraint, and that constraint is equal to 0, one constraint. What means that x, whatever x that you choose in order to find the maxima and minima, should be satisfying that inequality. So that idea of doing it through the method of Lagrange is brought to its most general form when you also include inequalities, but modern applications have inequalities as their hallmark rather than equalities, as you will very soon see, as you have seen already in the models that we have constructed, optimization models that we have constructed, that is the basic structure. Inequalities are the hallmark of modern optimization. So we are going to study the Karush-Kuhn-Tucker conditions, right? You all are aware in high school that we study, we take functions like this and we want to figure out whether this has a maxima and minima, provided the function f is also given to be differentiable. So what we do is we try to figure out what x would satisfy the equation that f dash x is equal to 0, the derivative at x is equal to 0. Suppose such a point is x naught. But this condition, you must remember, is a necessary condition and not a sufficient one. That is, when you get an x naught by solving this equation, it does not guarantee you that it is truly a local minimizer or global minimizer or local maximizer or global maximizer of this problem. And for that you need to talk about second order conditions, which you are aware in your school studies, high school studies. And now if I can take the second derivative, if I can't take the second derivative, then there is a big issue. If you can take the second derivative, then and compute it at x naught and see what happens. If it is strictly bigger than 0, you know that this will be a minimizer, local minimizer, local. The x naught is a local minimizer. Actually it is something called a strict local minimizer, but we are not going to get into those optimization, deeper optimization issues at this moment. Rather, for the course you did not get too much bogged up by those issues, and if this happens, then you get what is called a local maximizer. This is a repetition of what you already know from high school. This is just a recollection. Now, is this simple tool, simple idea or simple mechanism by which you can possibly find a maximizer or minimizer of a function from Rn to R, is this applicable when I additionally put a constraint? That is, if I say, okay, minimize a function say from R to R subject to x element of some interval, can I use the same idea to have it? The answer will surprisingly turn out to be no. For example, if you take the function fx equal to x square. So now you want to minimize it over the whole R. This is called unconstrained minimization. There is no additional restrictions on the from where the variable should come. It is free. So here if you look at the function y equal to x square, then at x equal to 0 you obtain the minimizer, and of course f dash 0 in this case is 0. But now suppose I take the same function y equal to x square, but I want to restrict it from, so now I want to choose x between 2 and 1. So it is the same problem, minimize x square subject to x belonging to the interval, closed interval 2 1. There is no doubt that you can look at the picture and immediately determine 1 as the minimizer or 2 as the maximizer. In fact, these are global maximizers. So now on this interval no longer x equal to 0 is present. So the minimizer here is 1. Now let me compute f dash 1. So f dash x is equal to 2x. This implies f dash 1 is equal to 2, not equal to 0. So if if you are looking at a constrained minimizer, it doesn't necessarily follow f dash x equal to 0. Here thus is a paradigm shift from going from unconstrained problem to the constrained problem. And here you see I have constraints in form of inequalities, and I could write this as x less than equal to 2 and minus x less than equal to minus 1. So there is a huge paradigm shift. So now question is, if I have a constrained problem, how do I write what sort of necessary conditions are being followed, so that I would be able to use those necessary conditions to at least compute a point which I can suspect to be the minimizer, and then test it through other conditions. So let us jump to higher dimensions, and that would make you have a much better understanding of what's coming. So in order to move towards the Karush-Kuntawar conditions, it is important that we again recall what would happen if I look at a function f from in a higher dimensional setup, that is a function f moving from Rn to R. Then how do you decide how to find a local maximizer or minimizer? In that case, your first step of course is to find a point x naught which satisfies the gradient equal to 0. Basically it is, gradient simply means del f del x1, so vector of n components, del f del xn. If I calculate them at the vectorial point x equal to x naught, that should give me the 0 vector. So find such a point x naught, that is all. But once I find a point x naught, I do not have much options, but I cannot say that x naught is a minimizer or a maximizer. But in many problems you can actually try to look into the problem structure and try to argue. But in many cases we have to rely on what is called second order conditions. Exactly progressing as we had done in the case of the function from the real line to the real line. The same idea has been progressed. But of course you are in a much higher dimensional setup, so things cannot be just writing bigger than 0, lesser than 0. So what you have to look into is the following. You have to know how to compute what is called the Hessian matrix of f. So the Hessian matrix is nothing but the Jacobian matrix of the gradient, or rather it is a matrix whose individual rows are the gradients of del f del x1 dot 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 del f del xn. So, if I take the gradient of del f del x1, so I take it with first with x1, del f del x1 square, del 2f del x2 del x1, del 2f del x1 del xn. So, I have taken the gradient of del xn del x1. I have taken the gradient of del f del x1. Del f del x1 is actually a function, right, from Rn to R. So, you have del 2f del x1 del xn. So, this matrix is a symmetric matrix provided if the function is differentiable, twice differentiable, and all these are continuous, then by Young's theorem this matrix becomes symmetric. Means if it is a twice continuously differentiable function, then the Hessian matrix becomes symmetric. So, those are some studied in some basic calculus. You should not be very much intimidated by this sort of expressions. So, once I find x naught, what I am supposed to do? So, again there are twofold paths. So, see if this is positive definite, and then again see and also check negative definite. So, if it is positive definite means that so you take any vector w and take this inner product, first operate f of x naught on w and then take inner product with w. If this is strictly bigger than w for all w not equal to 0, we call this to be positive definite. So, if this is 0, grad f x naught is 0 and this is positive definite, it implies that x naught is a local minimizer. While the opposite is of course true, you just have to change signs. And that would imply that x naught is a local maximizer. Once I know these two, so we have a complete picture of how to handle unconstrained problem. Of course, it is not always easy to find out this, but we still have a complete picture to handle unconstrained problem. Now, to begin the KKT story, we should go back to something more. Is there any the convexity story? So, here it is talking about finding the second derivative if that is exists, and then okay, you can do all these things. Can there be some other conditions on the function so that whenever I have this and x not satisfying this, that would give me a minimizer? In that case, one of the main assumptions on the function f is that of convexity. So, we are now going to look at convex functions. So, convex functions are functions of this form. So, f from R is convex if f of lambda y plus 1 minus lambda x is less than equal to lambda fy plus 1 minus lambda fx for all, this is a symbol of for all, the inverted A, for all lambda lying in the closed interval 0, 1. Of course, this simply means that this is an element in the line segment joining x and y. This is something you have already known in your coordinate geometry, in your basic high school. And also correspondingly there is a concept of a convex set. So C is convex if and only if, this is a symbol of if and only if, xy element of C implies that the whole line segment joining x and y would be inside C. Observe that here if I put lambda equal to 1, I would get y. If I put lambda equal to 0, I would get x. So as I move from 0 to 1, I change lambda from 0 to 1, I am actually moving along a straight line from x to y. So a major idea, why convexity is important? Convexity is important because if you want to minimize a convex function over a convex set, that is constraint optimization in fact, then there is no local minimizer, every minimizer is a global minimizer. So if you put, our whole space Rn itself is also a convex set. So we will largely be bothered about functions from Rn to R, because in the literature you can also talk about functions from a given convex set C to R and see whether they have this behavior. Convexity from a more geometrical point of view means the following, means that if you have a convex function and if you take 2 points on the graph of the function and if you join them by a chord, that chord would always lie above the graph of that function, lying between these 2 points. So the portion of the graph of the function lying between, say, this point and this point will always lie below this particular line segment joining these 2 points. That is exactly the meaning of this statement. So what we are now going to show is that if you have convexity, right, if you have convexity of the function f, then you do not have to look for second order conditions. The reason is this: suppose I have a function which is differentiable and convex, then we have a following nice expression that f will satisfy a following nice inequality. F is differentiable and convex if and only if, so I didn't write IFF but wrote the whole thing, if and only if fy minus fx is greater than equal to the gradient of f at x in a product with y minus x, and this is for all y element of Rn. We are just bothered about convex function from Rn to R. So what happens, suppose, so this will be, so if I fix up an x, for whatever y I take, this will be true. So if x naught be such that grad fx naught is equal to 0, employing this inequality, it will mean fy is greater than equal to fx naught for all y. So this is a very, very important thing, that for a convex function, so minimize, if you minimize f convex over a convex set C, then local is equal to global. And every local minimizer is a global minimizer. This is a very shorthand way of writing. Don't think that I have written some mathematical equations, local equal to global. It's some small, just a simple way of writing. So, we will now come to the constraint case and explain to you what is the Karush-Puntakar conditions. So, now as we promised, we will start our discussion on the constraint optimization problem. Here we will not focus on this any general structure, but a standard structure. So, this is the one we had already written down. In the last class. However, we are not going to include x element of capital X. We will not going to include abstract constant. We are going to take this most simple format, and then we are going to discuss what sort of conditions these would follow if we have a local minimizer. We are going to speak in terms of minimizer only, as I have already told you. In finance also, you are essentially minimizing your risk in the optimization models. So, let us listen here, that here we would assume f, gi, hj are all smooth. Smooth means continuously differentiable. They are differentiable, and then the partial derivatives are also continuous. Now, once I do that, and suppose x naught is a local minimizer, then what? So, if x naught is a local minimizer, what sort of conditions do x naught satisfy in terms of the given data of the problem? So, it was Fritz John in 1948. Fritz John is one name, it is not two names. Usually some people also call it the John conditions. He wrote up a paper giving the necessary conditions and also used it to devise certain algorithms and sent it to Duke Journal of Mathematics, which rejected it, and later on he published in some conference proceedings. But this is one of the most fundamental conditions that we need to know when we study some basic optimization. Fritz John conditions do not require any additional condition. It tells, okay, if you have smooth functions, this is the problem, x naught is a local minimizer, then this will happen. But Fritz John says that if x naught is a local mean, then there exists scalars lambda naught, which will be associated with the grad of f greater than or equal to 0, lambda I, which will be associated with the grad of g's, and mu j's, which is just an element of R, it could have any sign. So, this is a sign called there exists. Those who are not familiar with mathematical symbols, this simply means there exists. So, there exists scalars. So, there exist scalars. This of this nature. You see, when you have inequalities, you have sign on the so called multipliers. These are something like the Lagrange multipliers. So, then they are scalars such that lambda naught grad of fx naught plus summation I is equal to 1 to m lambda I grad of gi x naught plus summation j is equal to 1 to k mu j grad hj x naught is equal to 0, and lambda I gi x naught is equal to 0 for all I, equal to 1 to n. So, this is the standard optimality condition, and lambda naught, lambda 1, lambda m, mu 1, mu k, this full vector cannot be a 0 vector, means all of these cannot be simultaneously 0. If all of these are simultaneously 0, it obviously satisfies this condition. So, you have to find a vector where they are not all simultaneously 0 and they satisfy this. This is what Fritz John proved in 1948, and this condition is called the complementary slackness condition, a very important tool in optimization, very important notion. This simply means that you cannot have both of these holding with strict inequalities at the same time. You cannot have lambda I strictly bigger than 0 as well as at the same time gi x strictly less than 0. This is not possible, because if lambda is strictly bigger than 0, gi x naught must be equal to 0. That is the way it is, because then you will maintain this inequality, and this is very, very fundamental. So, the drawback, however, of the Fritz John points was that lambda naught could be 0. If lambda naught could be 0, then the role of the objective function goes away from the problem, and that is something you wouldn't like. And there are many, suppose if I now employ some convexity hypothesis on the f and g's, then unless I know whether the lambda naught is strictly bigger than 0, I have no way to prove that under such conditions x naught will again give me a global minimizer. And there could be feasible points which are not optima, they can still satisfy the Fritz John condition. The Fritz John condition has a very important role, is that it provides a negativity certificate, that is, in the sense, negative certificate, that is, if there is a x naught which violates the Fritz John condition, then it is definitely not a local minimizer or global minimizer. So, how to devise a condition where these anomalies of Fritz John condition, rather like lambda not becoming 0, goes away, and that was framed by Karush, Kuhn and Tucker. So, originally framed by Kuhn and Tucker in 1951 and published in 1951, and then they found that Karush had already done some work of a similar type in his MS thesis, and then Kuhn wrote to him and they got the historical facts straightened. So, Kuhn and Tucker 1951 is the paper which everybody would refer to. What they say is the following. So, you have the same conditions. So with the Fritz John condition, add with it some conditions on the constraints, that is called constraint qualifications. And once you do that, you can show that by choosing a proper constraint qualification that lambda naught is strictly bigger than 0. And then you can divide everything by lambda naught, and then you get new multipliers where these conditions would be maintained, and the Kuhn-Tucker condition would look like grad f x naught plus lambda I dash grad gi x naught plus mu j dash grad h j x naught. So, this can be normalized to 1. So, basically once you know that lambda naught is strictly greater than 0, divide whole thing both sides by lambda naught. So, that is what is Kuhn-Tucker condition. Fritz John condition plus and constant qualification will give you this. Suppose I say that okay, I am in a situation to check that all the gradient vectors of GIs and all the gradient vectors of HG are linearly independent, then you can easily show that lambda naught is strictly greater than 0. So I would rather ask you to go to the web and figure out what sort of constant qualifications are there. Now, the importance of Kuntaker condition comes when you are talking about convex functions. So if f is convex, if GI is convex and Hj is affine functions were all discussed when we were talking about linear programming. Hj is affine and KKT condition holds at a feasible x naught, then x naught is a global maximizer, a minimizer, sorry, x naught is a global minimizer. So I would like that at home you would write down, figure out what are constant qualifications, and then you can show mathematically, you try to show mathematically, okay, if this is happening, then lambda naught would be strictly greater than 0. I can divide all sides by lambda naught, basically choose lambda naught equal to 1 and then write down the Kuntaker conditions. So with this I would end today's talk, and when we start next week, we really start with hardcore finance. We will talk about portfolio optimization, and that would be due in 2 parts, and then we will go to the capital asset pricing model. Thank you very much.